Good morning, everyone. I want to welcome you all to this winter semester. I'm your instructor for General Physics 2, the 74152 course. And my name is Dr. Charity Adaizenemuwe. Some of you already know me. I instructed the General Physics 1, and we're just going to be continuing from where we stop on General Physics 1. In General Physics 1, we stopped at chapter 13, so we're progressing from chapter 14 to chapter 28. So we're covering chapter 14 to 28 of our college physics textbook, the 4th edition. Understand that some of us make use of a previous edition. If you're one of those using previous edition, you should please endeavor to take your assignment from the current edition and not solve the wrong problem like it was in the previous cases. Okay. So as usual, we'll be having updates on Moodle concerning any changes in our classes. Our class is supposed to be in person, but for the first few weeks, we'll be having it online, and the first few lectures also will be pre-recorded. So we'll begin today's class from chapter 14, which is oscillation. Okay. So before now, we've been describing motion that have definite start points. We can actually state categorically that this is the beginning of a particular motion we're describing, and this is where it ends. For example, we can say that a car is starting from rest and is coming to a final velocity or position at points A, B, C, D, and so on. We can also do that for the description of temperature, that we started at initial temperature this and ended at final temperature. But when we come to talking about oscillation, we cannot actually say for certainty that this is the start or the end of the motion we want to describe. So the dynamics of such motion that we cannot tell specifically their definite start and end is what we want to discuss under the topic oscillation. And like we see the picture in this image, the motion of the gabion swinging over its the pivot, which should that will be the pivot, using the hand to swing across the water on that tree. This kind of motion for animals, objects, and so on is what we'll be looking at. And our goal is to understand the system that oscillates with simple harmonic motion. We have systems that oscillate that does not really follow the simple harmonic motion trend, but our focus would be to look at system that oscillates but follows the simple harmonic motion. Okay, so we are reducing our discourse on oscillation to motion relating to simple harmonic motion. Okay, so we'll be covering 3 major blocks. A motion that repeats itself, we talked about general oscillation, and we'll discuss it in relation to simple harmonic motion, and also talk about the resonance, that is the oscillation at its natural frequency. All right, so the rhythm of the course is going to be similar to the rhythm of the General Physics 1, for those of you who took the General Physics 1 with me. And for those that are just taking the class now, the rhythm, what we mean by the rhythm of the course is that we'll be covering a chapter in a week. So by the end of the term, we would have covered from chapter 14 to chapter 28. Okay, So this week 1 of our class, we'll be covering chapter 14. So now we'll also be understanding first, this class is like an introduction of what the discourse on oscillation is, and we'll just go a little bit deep into the subject. So, but first we'll have to look at certain terminologies that we can use to describe or understand what we mean by oscillation and its relationship with simple harmonic motion. Some of these terms are terms that we already know. So we're just going to just say them like a reminder, but not dwell on them so much. Okay. So we'll look at the first one, which is the equilibrium and oscillation. Now we know that when we talk about equilibrium, we're actually talking about primarily something that is the rest point or a balanced position. So how does equilibrium relate to oscillation? We actually use the idea of equilibrium to describe oscillatory motion. So let's see quickly the figure before us that I want to use to understand the subject equilibrium and as it relates to oscillation. All right. Oscillation primarily is motion that is repeating itself, motion that can actually go back and forth repeatedly. So whenever we see such motion, we say something or that object is oscillating. So let's look at the example before us here now. The figure A and B describes the equilibrium position and how we use that to describe the oscillatory or oscillating motion. So the equilibrium and the restoring force of the ball is what the figure A is showing to us. When the ball is at rest, this rest position is what we call the equilibrium position. Now, if you tilt the ball to your right, the net force tends to drag it back down to this equilibrium position. And when it gets to this equilibrium position, the inertial force, you know, the law of inertia, Newton's first law, takes it further beyond the equilibrium position to this side as well. And then the net force tends also to pull it back to this position. And when it gets to the equilibrium point again, the inertial force takes it further. All right. So this tends to repeat itself. This will not stop until an external force is acted on that ball to bring it to a stop. So if we look at the free body diagram of this description, we see the net force acting to bring back the ball to its equilibrium position. We have the weight of the ball, and then we'll have the normal force on that ball. So if we look at the diagram in figure B, where we use the idea of equilibrium position to describe oscillatory motion, we'll see the same analogy here. What the ball is undergoing when you tilt it at a velocity towards the right and it begins to roll, you see that when the ball is released, a restoring force pulls the ball back towards its equilibrium position. And this restoring force is what we are calling the force net or net force. And we said that when it gets to this position, the force of inertia causes it to go beyond the equilibrium position. And then the net force again act on it, making that ball to roll endlessly in the bowl. Okay, and the kind of motion is going back and forth. And that kind of motion is what we describe as oscillation or oscillating motion. Okay, so we'll see that the marble ball actually is undergoing oscillatory motion. and we'll use the equilibrium position to better describe the displacement from rest, okay? And we know that the displacement from rest for an oscillatory motion has its description, and we looked at that. We see that also when we start using the terminology to describe it. But practically we say it's the amplitude, but at different instances, we may not choose to call it amplitude, okay? So whenever we have motion that is repeating itself, just like that which we just saw, or motion of a pendulum, any motion that is going back and forth, we can actually characterize such motion using terms like period and frequency. And we discussed this previously in chapter 6. Period and frequency's definition did not change, and we'll just quickly look at the definition as a reminder. We know that period and frequency have relationship in the sense that one is the reciprocal of the other. Okay, so period, which is simply the time it takes to complete one full circle, is called the period, and it has a symbol T with the unit seconds. While frequency is actually the number of circles completed in 1 second. That's what we mean by per second. And the unit for frequency is S. Now, the relationship between frequency and period is such that they are reciprocal. One is inverse, the inverse of the other. Okay, so frequency is 1 over T, or T is 1 over frequency. This is just a simple diagram describing the ECG result of a patient's heartbeat. We see that it's following a particular or predefined interval. So from this peak to this peak repeatedly is the period. You can choose to use this peak if you want, but as long as you can point out clearly the repetition in such motion. Okay, so let's quickly see how that we will use the relationship between frequency and period to solve problems. Let's quickly look at the example. An FM radio station broadcasts at oscillating radio wave at a frequency of 100 megahertz. What is the period of the oscillation? They gave you the frequency and they're asking for the period. So you just apply the formula for period to that, which is the inverse of frequency. So 100 megahertz is simply 1 times 10 raised to the power 8 hertz. And if you take the inverse of that, you will see that the result is going to give you 10 nanoseconds. Okay, so we'll have an example here to remind us of what the mega, the kilo, and the giga units are, and also their equivalent in terms of period, the milliseconds, the microseconds, and the nanoseconds. Okay. So we said at the beginning that we want to focus on oscillatory motion that actually can be described with simple harmonic motion. So let's quickly see what simple harmonic motion is exactly. Simple harmonic motion is a special kind of motion typified by the back and forth oscillation. Okay, it is typified by the repetition of a particular kind of motion over and over. Most especially, it can be described as the back and forth motion. And worthy of note is the fact that the graph of an object in simple harmonic motion is sinusoidal. Now, when we say the graph is sinusoidal, it simply means that we can actually use the sine and the cos functions to describe that graph. So if you look at the image before us right now, we bring to mind again the image or the description of the marble ball in that bowl that we saw earlier when we were describing oscillatory motion. Now, if we happen to plot the several positions of that ball on a graph, remember the ball was at rest here and it was tilted to this maximum position at a particular distance. If you plot the position graph, it started from rest point 0. Tilting to the right means positive and tilting to the left is negative. So that's how we know that the ball is at the positive position here. And then it goes back to a rest position 0. And then it goes again to the left, which is a negative position, coming to the same displacement as to the right. So we'll have a peak here on the negative side. And then it comes back to the rest position, then goes back again. So we'll have full complete circle here. Okay. So this description is actually the description of a simple harmonic motion, because we can see that the oscillatory motion have the defined pattern and a period from where it started to coming back to the position where it started. That time is actually what we call period. Okay, we'll have other simple harmonic motion example like the car bouncing on the spring, mass on a spring, we'll have vibration in the air, we'll have the pendulum, we'll have the motion of your leg while walking, which we'll be looking at in other later part of this chapter. So we already established or defined simple harmonic motion, oscillatory motion, and we'll also be looking at some other terms when describing forces and simple harmonic motion. But before then, let's quickly take this activity to check our understanding. Two oscillating systems have period T1 and T2, and this is the relationship. T1 is less than T2. The question now is, how are the frequencies of these two systems related? You already know the relationship between frequency and period before to be what? The inverse of the other. That means the inverse relationship of this is what they'll have. And that's why our option was C. Because if T is going to be less than T2, that means the frequency is actually greater than T2. That buttresses the relationship that they are inversely proportional to one another. Okay, so let's look at the description of force and simple harmonic motion. We'll start with the linear restoring force. We have seen what we call restoring force before, that force that we described as net force when introducing oscillation. We describe that as a force that brings back the object to its equilibrium position, then to pull it back to rest position. Okay, so with the word linear tells you we're going to be looking at that force only in a straight line direction. It could be on the x-axis or on the y-axis. Okay, so let's look at how that force can actually be related or described with simple harmonic motion is what this experiment wants to emphasize to us. We'll look at the air track glides on this spring. This is the air track. This is a glider. And at this position, we describe this position as position where the net force is 0, the object or the glider is at equilibrium here. Now you can choose to pull it, spring to the right or to the left. Remember, we said a pull to the right is positive and a pull to the left is negative. Okay. So if you pull, for example, this glider at the distance change in s towards your right, you see the spring will stretch, right? And it goes from rest position to that. If you release it, the spring force is going to act to bring it back to that position. And when it comes to rest, the inertia will push it further and you will see something like a back and forth motion. Okay, and that back and forth motion is described actually by simple harmonic motion. It's the same as what you have seen earlier. So we can actually bring in our understanding of the Hooke's law to describing this. You know, the spring constant is actually expressed in this formula, the spring force expressed in this formula with the K being the spring constant. And the negative sign simply tells you the direction of the force of that spring is going to the left because it's going to be restoring the glider back to equilibrium position. So that is why we have minus here. But in some cases, we will not have the minus. So we have that this net force that tend to bring back the force and that spring back to the position is what we call the linear restoring force. Okay. And we also have, we'll look at the linear restoring force. We just saw one that can be described on the x-axis. Let's look at the linear restoring force when we describe it on the y-axis. And we call that the horizontal motion on the horizontal motion of a mass on a spring. Okay, it's simply the same description, but please take note of the signs and the expression used here. Okay, so if you see us use different expression, we are trying to describe the same motion, but in on different axes or plane. So you see the motion on the horizontal describing exactly what we've just seen. We just brought out the amplitude to show to us. The displacement, this is actually the oscillatory part, the back and forth part. If we pick the rest position to be 0, a displacement to the right is equal to the displacement to the left, while the signage actually tells us the direction of that displacement. Okay, so when we make the graph of that motion, we're going to see something like this. It's a sinusoidal graph at different peaks for the positive and the negative, and this is the rest position. Okay, so we just brought in the concept of amplitude to describe, you know, in the first case, we expressed Hooke's law with the change in x being the displacement. But actually, when describing simple harmonic motion or oscillatory motion, we use the term amplitude to describe the maximum displacement from its rest position. Okay, so we'll have the positive amplitude and the negative amplitude that emphasizes the direction of that displacement. So oscillation about an equilibrium position with a linear restoring force is always a simple harmonic motion. And that is how we connect the force and the simple harmonic motion. So let's look at the vertical motion of the mass on a spring. We just looked at the one that described the x-axis. Let's see what happens if it's on the y-axis. Will it be a simple harmonic motion as well? Are we going to be using the same expression for Hooke's law to describe this? Let's see. So we'll see the figure. The equilibrium position of the mass is described here. So when the mass is on stretch, we have when we added weight and it stretches to a new rest position. And then we'll have that change in length. That stretch, we use the change in L to represent the stretch. Okay, so this stretch, the weight is pulling downward, but the restoring force from that spring is going upward, which is positive. So we have from Hooke's law that there's no minus in our expression here. Okay, So from Hooke's law and using Newton's first law to describe this stretch, we have the net force to be equal to the force of the spring plus the weight force, which is equal to this expression, which is K change in L, minus, weight is always pointing downward and it's negative, mg, which is equal to 0. Because for it to be equal to 0, it means it's at the rest position as well. If you want to get the simple harmonic motion, you can pull further or let it spring up. You will see a back and forth motion also. So from this expression, we can actually say that K change in L is equal to mg. And if you make change in L the subject of formula, that's when you have mg over K. Okay, so what we just did was to first say K change in L, move this to cross the sign of equality, it becomes mg. All right, then you divide both sides by the coefficient of change in L. So that's how we got this expression here. Okay, so this expression is actually the description of that spring stretch that happens when you put an object on the spring to get a new equilibrium position of that object. So that stretch is actually mg over K. Okay. So if we have a distinct description, when after you hang the ball, we have this position being the equilibrium position, and you want to create a simple harmonic motion, you pull. If you pull this after stretching, this is the equilibrium position. When you pull this with a distance or shrink it with a distance y away from this rest position, we will have the new stretch to be changing L, that is this one, minus this. That's where we have this. Okay, and so the free body diagram for that motion will be something like this. The net force tends to come back down, bring the object back to rest, and the initial force or gravity pulls it further down, and then it starts springing forth and back. So if we use the Hooke's law again, which is K, force constant or spring constant as a product of displacement. This is the new expression for our displacement. So that's why we have K changing L minus Y. So to get the net force in this system, we have that the spring force plus the weight. This is the formula for the spring force as described from Hooke's law minus the weight. What we did was to open up the bracket here. K change in L, then K minus Y. So you have something like K change in L minus Ky minus mg, which is equal to this expression here, ky. So rearranging this, that's how we got the expression there. Okay. But we know from the expression we saw for change in L to be mg over K, we also know that change in L minus mg was equal to 0. That's how we were able to get this. So if we establish, having known that change in L minus mg is equal to 0, we can actually equate this place to 0. Therefore, we'll be left with the net force being equal to spring constant multiplied by this moving object upward or downwards. So we see that the final or net force for the horizontal, for the vertical, is minus spring constant change in distance, while that of the horizontal is minus spring constant change in the x-axis. So we're just describing the same thing using the different axes. Okay. So let's see another motion that describes the simple harmonic motion, which is the most common one, the pendulum. Okay. We'll look at the pendulum again later, but let's just quickly introduce the pendulum as an object or pendulum system describes the simple harmonic motion, which is also about the displacement of objects away from their equilibrium position. So we'll see the figure A and B here describing the motion of force on a pendulum with the bulb and mass. Okay, so the same way we'll be describing oscillation, we'll definitely have a point where we'll say it is the rest point, which is the equilibrium position point. And if you pull the ball that's resting on the point 0 to the right or to the left, depending on which one, remember, right is positive, left is negative. So we tend to always put the right to have positive values first before we use the left part to complete the swing or the period T. So we have in describing simple harmonic motion for the pendulum, we have the arc length S. We have seen this before also in chapter 6. We'll have the arc length x, and we'll have the length of the rope, and then the angle it made to the center of that circle. So if we use the free body diagram to describe that motion in the figure A, we see that the tension, remember the force on tension is always acting in the direction of the rope towards the center. So the tension does not have a tangential component because it's acting towards the center directly. But the force which is pointing down has a tangential component. And the tangential component is described with the expression, the weight minus W, which is the weight, sine theta. Okay. Now, we see that the tangential component of weight is actually describing the arc x. Okay. So we can actually kind of establish a relationship there, which we'll see later. So in this kind of system, the net force that tends to pull back the ball to its rest position is actually the tangential component of that weight. Look at it. That's what is pulling it back to the position. Not the force on the tension, not just the force on the weight, but the tangential component of the force on the weight. And that tangential component is given as minus W sine theta from the so that's why you'll be able to tell to find this, you're going to use sine, which is opposite of hypotenuse. So that is how we have the relationship that theta is actually equals to S over L, opposite over hypotenuse. And we saw that in the previous chapter 7. Okay, so net force, the force I'll bring back the ball, is equal to the total force of the system, which is equal to the force of the weight, and is given as minus W sine theta, which is mg, minus mg sine theta. And this is true for small angle displacement. When we have small angle displacement, sine theta is going to be approximately equal to theta. That means the displacement in the description of theta, not amplitude right now. Remember, in our circular motion, we use theta to describe the displacement. Good. Displacement, this understanding of displacement will actually modify our equation for net force, Therefore, our net force of seen is equal to minus mg sine theta. And if at small angle, sine theta is equal to theta, so we'll have minus mg theta. Putting the value this into theta, we'll have minus mg s over L. So we can actually look for the length, the arc length, the length of the rope, arc length, and compare them to the weight or the gravity as it relates to the net force there. So we want to establish that the force on a pendulum is a linear restoring force for small angles so that the pendulum will undergo a simple harmonic motion. If the angles become larger, we're not sure what we'll be having is simple harmonic motion because we'll be having lots of, which a concept we will see later, the fading effect, that the motion or the amplitude begin to reduce, and then we will not have a clear description of what the simple harmonic motion is in that kind of motion. So the restoring force, remember, is actually proportional to displacement. So let's see how that statement is true. A ball is hung from a rope, making a pendulum. When it is put 5 degrees to the side, the restoring force was 10 Newton. What would be the magnitude of the restoring force if the ball was put 10 degrees to the side? Now, when it was put 5 degrees, it was 1 Newton. So if you pull it twice, you should be able to get twice the effect of force, because we have stated that force is actually proportional to displacement. So that is why D was our choice of answer. Okay. So let's use a few minutes remaining to see the description of simple harmonic motion. We've already seen simple harmonic motion as an oscillatory motion. We've seen simple harmonic motion description of forces and how they relate to back and forth motion. How exactly do we describe simple harmonic motion? It's nothing different from what we've been seeing, but it's just simply the introduction of the use of period at different times. Okay, that is the unique thing about the subject describing simple harmonic motion. We have been describing it, but we just want to put a digit or a figure or an equation to the position description, acceleration description, velocity description. Okay, so for a full circle, according to the marble ball description that we've seen several times, or the pull of the ball on a spring, in this case, the vertical one, you see the point where it started and the point where it returned to where it started is one full period. So it started at point 0, t equal to 0, and it's going to end at t being the period of that oscillation. So if this is a rest point and up is positive, you pull it at an amplitude y being equal to a, and you release it. Just when it's heading back to the rest point, you see the velocity coming up for the first time, and immediately it passes the rest point, or on the red point, the velocity is at maximum. Then it begins to reduce as it approaches the negative amplitude, which is the displacement A, in the negative direction. So you see it go back again in the same trend. Immediately it crosses, it has a maximum velocity, and then it comes back. Now I'm emphasizing immediately it crosses because that is how you'll be able to tell the position of maximum velocity and acceleration as well. So we'll see when t is at 0, we can see when t is equal to quarter t, that is when the ball is immediately after, that is making the first cycle, after the rest point. So immediately after the rest point, which is 1/4, and if it's coming back, it's going to be 3 over 4. So if I've been describing a motion before, and what we can tell the number of circles, we can actually use the 3 over 4 part to describe the immediate position after the rest point. Okay. So we see that if we make a plot of that, the position time graph, which remember I said they are sinusoidal functions. They are functions that we can use the cos or the sine curve to represent. So the position time graph tend to be similar to the acceleration time graph, but in the inverse manner. While the velocity time graph is not in sync at all with either the position or the acceleration. When the velocity is at maximum, the acceleration was at 0. So it's that different. And how do you know this? When it's not starting from rest point, this is cos. When it's at rest, starting from rest point is sine, and this is cos. So just keep that trick in mind. So to describe the equation that we use to derive this, that the position graph, the velocity graph, and the time graph. We'll look at that in the next slide, but we want to emphasize that the position graph is actually a cos curve, or a cos function of 2 rad, which is 360 degrees. So we'll arrive at the distance or displacement t is equal to amplitude A cos 2 pi t small t over big T. So to make the formula shorter, we bring in the concept of the proportionality of period, which is the frequency. We just take the inverse to bring in our f into the equation. So we'll have for the position A cos 2 pi ft, f for frequency, t for time in seconds. While for the velocity graph, it's a sine graph. So we have, it started from the v minus, the down part, that's how we have it here. If it was v starting on the v plus like you have in the position, we'll be using the positive. Okay, so we did the same thing, bring in our f to reduce it to a linear expression. In that, for acceleration, we started with reminder of ourselves from the second law that f is equal to ma, and bringing that into this description, we'll have the negative acceleration as well, which is negative mass cos 2 pi t over t. T time in seconds over time, big time period. Okay. So let's see the class activity to see if check our understanding on that. We will not dress too much in explaining this class activity. I have it explained in the last slide. So we'll have a graph in the table as it applies to that graph shown in simple pendulum. So we're asking you to check the graph because that is the same description we have. So the period of that graph is specified to be 2 seconds. When you pull the pendulum to the right, which is the positive side, and let it go, it's going to go back to the same position on the right, ideally. Okay. If there's no damping or if there's no damping effect to the swing, or if we can ignore air resistance, it should get back to that maximum position. So we're asking first, when will be the first time it will hit the maximum negative displacement? Maximum. So when it was coming down, because you pulled to the positive displacement, which is to your right, when it was coming back, the first time it will hit the maximum displacement, when will it be? We have the period already. And from our chart, the first time it's going to hit, look at it. The first time it's going to hit the maximum negative displacement is here. Okay, so we'll have t equal to 1 over 4. And that's what t equals to half. That's what we use to describe this. We use the different time period position on a period 2.0 scale. Okay. So A, B, A, C, B is the answer for that. This is simply the graph of sinusoidal relationship, which we have already said that when it starts from origin, it's a sine. When it starts from either here or here, it's a cos. Okay. A cost function description and a sine function description. And these are the equivalent magnitude positions that we can think of from the chart. So let's quickly look at example before we have just 4 minutes. Example 1, an air track glider oscillates horizontally on a spring at a frequency of 0.50 Hz. Suppose the glider is pulled to the right of the equilibrium position by 12 cm and released. Where will the glider be at 1 second after the release? What is the velocity at that point? Good. So first of all, we want to visualize what the description of motion is here. If we look at this figure here, it was pulled to the right, which shows you it's positive. So at position where 12 cm, that means minus 12 cm, because if it's coming back with the same force, and we'll have approximately or equal to the displacement of 12. So we'll have the range of oscillation to be 12 to minus 12. Okay. So having visualized this, we try to solve. Then we look at the graph for the comment on the velocity at that time. So they gave us a frequency. We can actually look for the period, which we did to obtain 2 by taking the inverse, which is 1 over f of the frequency given to get the period. When we did that, we got the period to be 2 seconds. So it means at 1 second, it's already halfway into the journey. So we just divided the journey into 2. And then we saw the peak of the position. And that peak simply tells us that at that position, velocity is 0, remember. That means the position where it's just about to return back to its equilibrium position. Okay. So another thing we want to look at is connecting simple harmonic motion to uniform circular motion. Can we actually, apart from the back and forth motion, describe other phenomena as simple harmonic motion? Yes, from this experiment, we can actually describe uniform circular motion to be on a plane with a band of oscillatory distance. And we'll be able to prove that actually circular motion is actually a simple harmonic motion or oscillatory motion within an oscillatory band parts, which is as defined by these 2 arrow head. Okay, so if you place the ball on a turntable and shine your lights on the ball, make it such that it projects on the screen, you see that when the ball is at one position, it's going to be showing here. As it's rotating, it's coming to this side and going here. So before you know, you are seeing the back and the forth motion of that curve. And that is simply simple harmonic motion. So we can actually use the simple harmonic motion to describe the circular motion in one plane. Okay. So both circular motion and simple harmonic motion are motions that repeat itself. So we can say there are some circular motions that are actually simple harmonic motion. So the uniform circular motion projects onto one dimension in specific, in simple harmonic motion. If we project it to one dimension, we will have exactly the the same description of a back and forth simple harmonic motion description. Okay, fine. I want you to record this description, keep it in mind, while we use it to determine some equations that we'll be needing to solving some problems. So first, we're going to, from the graph, describe the position, velocity, and acceleration. From the position, this is the screen plane. At different position, the ball will be on a different position on this plane. So the ball at this position right now, we describe that position as A, which is amplitude or displacement, cos phi. Okay. So for the velocity, we use 2 pi fa, the relationship which we have seen in the previous chapter as well, to describe the velocity. And the acceleration also, which is simply the square of the velocity and the amplitude A. Okay, so we have the description for position, the description for velocity, and the description for acceleration. Okay, so at the position distance, we see the acceleration is going this way. So it's heading to the left, and then we'll have some negative signs to show you the direction it was heading to. Okay, remember those signs are majorly directional, they're not affecting the magnitude. So we didn't have to make a plot. We just brought out the plot describing the position, which is similar to what you have seen before. We see this and this are similar, but they are inverse. Okay, so the maximum point equation is always our cheat to understanding and using them to solve problems. Okay, but note that the position for simple harmonic motion is simply x maximum equal to the amplitude. So the amplitude is actually the description of the displacement at maximum x. Okay, let's see the second example and then we'll be done. The John Hancock Center in Chicago is 100-story building high. Strong wind can make the building to sway, so it can cause with all tall building. No, sorry. Strong wind can cause the building to sway, and this is the case for all tall building. Now the question comes up. On a particular windy day, the top of the building oscillates with an amplitude of 40 cm and a period of 7.7 seconds. What are the maximum speed and acceleration at the top of this building? Maximum speed and acceleration, what was given? They gave us the height, they gave us the amplitude, which is the A, and they gave us the period. Good, and they're asking us for what? Maximum speed and acceleration on the top of that building. Okay, so since the frequency is given and the amplitude is given, you can actually, the period is given, you can actually obtain the frequency from the period. Then approach the first equation that says the maximum speed. We have the equation for maximum speed, and that is what we will use. We just apply this equation to it. So applying that equation, we have 2 pi, which is a constant, the frequency we have determined, and the amplitude given. And we can tell that the velocity is going to be 0.33 meter per second. Okay, and the maximum acceleration as well, which we got from the equation formula, substituting directly, we will have the maximum acceleration to be 0.27 meters per second. You see, they're so short. The question seems to be too plenty or cumbersome, but the answer is very straightforward. Let's take this last example and we'll call it a day. A classic children toy consists of a wooden animal suspended from a spring. If you lift the toy up 10 cm and let it go, remember you're hanging it on the spring, it will gently bob up and down, making an oscillatory motion. So completing 4 oscillations in 10 seconds. They're giving you period, so you can actually manipulate this one to get a frequency and to approach the problem. What is the oscillation frequency? What does the toy, when does the toy first reach its maximum speed? And what is this speed? What are the position and velocity? What are the position and velocity at 4 seconds after you release the ball? Okay. So to begin, we visualize first what happened. We have 4. It was specified here in the question that we have 4 oscillation in 10 seconds. So we have 1 oscillation, 2, circle this oscillation, 1, 2, 3, 4. Okay. So we have that t equals to t over 4 because it's happening at the 4 seconds after. All right, so we approach the solution, we visualize it, and then we establish the parameters we are looking for. The maximum displacement is actually 0.1 meters because it's 10 cm. Okay, so in solving this, we use the information we have to look for the frequency. So the period is 2.5 seconds. So the frequency is the inverse of that. So we have 0.4 hertz. So we have been able to calculate the frequency. So we look at the B part, which is the position graph. So to do that, we have to remind ourselves on the picture we just presented before, where we use T half, T quarter to describe the position. The question says the maximum position, the first maximum. Okay. So we use, for the P, maximum speed. We use the equation for maximum speed to solve that problem. So using this equation and substituting directly, we have 0.25 as the maximum speed. And the C, which is where with the velocity be and the position at 4 seconds. Remember, it's completing how many oscillations in 10 seconds? 4. So if that is 2.5 per second, okay? So that means that complete 4 is into its final stage. So if we bring that in, on the x-axis, will be on the y-axis, because all the forces on the y-axis, we'll have a cos 2 pi ft. So substituting a value into it, we see that displacement is actually a minus because the pull was which direction is pull? I've forgotten. All right, one moment. So the velocity at that position, using the equation for maximum velocity, will have v minus v sine f pi 2 pi ft. If we also substitute directly from the parameter given, we'll see the velocity to be, but this is the distance, sorry. I kept saying velocity the first time. So we'll see that the velocity is 1.5 meters. Okay. So we'll have some practice questions here as usual, and then we'll begin our next class on energy in simple harmonic motion. And we should be able to round up the chapter 14 of our class this first week. Okay. Thank you so much. I know it's been a long one having to listen, but I want to encourage you to consult the textbook. And if you have any question, as usual, feel free to reach me. Feel free to send me an email. Ask for clarity when you need one. All right. Thank you. Have a great day. Bye-bye.